Welcome everybody. This is a new format for me, but excited to be here. So I'm going to talk today about some kind of old-time algorithms that show what you can do in distributed storage, and these things are becoming relevant in practical systems, but they'll cover more the fundamentals than the actual implementations. And to start off, the question, when I try to explain to people who are not from the area what they do, I ask them, where are your files? And, people once used to say, well, they're on my computer or on my server or, my laptop. But now, everybody knows, even young kids, if I ask where are your files, they say, of course, they're in the cloud, right? Everybody's files are in the cloud. And then the question is, what's going on inside the cloud? Where are the files inside the cloud? Is it like a big server there sitting on the cloud where everybody's files are? Or, how does it really work? So I tried to look for some very schematic picture describing what's going on inside the cloud. So this is a fairly dated picture, as you can see by the graphics, and it kind of shows the general idea of how things work. The cloud is not one machine, obviously, and the data itself resides on a collection of servers. This is what you see at the bottom here in the blue tier, and then there is a collection of servers. They're called web servers here, but other places they're called front ends, that communicate to the clients and retrieve their information, and some kind of a load balancer trying to distribute the requests of the clients to the servers and to return the results. So this is a very nice, beautiful picture. But then, if you look at more up-to-date pictures of architectures that are being used in clouds today, you find pictures like these. And a lot of the technologies mentioned in these pictures, like HBase and Swift and etcd and Zookeeper, these are kind of things that I've worked on over the years. But as you can see, there's a big collection of things, and every one of them does one little thing. And I think my favorite picture that I found that describes this really well is this one, actually. Yes, very complicated. So my goal is to try to go back to the fundamentals and to try to explain, the basics of how your data is going to be stored in the cloud, how it's going to remain persistent and consistent, and so on, and to mask away all these tiers of complexity that happen later. Just a little bit of a historical note. Distributed storage became really popular when Google started building their servers. They said, well, we can build something very cost effective. We can have many cheap, low reliability storage nodes, and we're going to provide reliability versus redundancy. And that's when they started introducing file systems like GFS, and we saw other companies introducing technologies like Cassandra and other related storage kind of grew out of that concept. So what I'm going to discuss today is the theory that predates this technology, but that's how this technology started emerging in the real world. And the premise for all of this, for all of these file systems, and also for the algorithms that I'm going to describe, is that failures happen. And actually, I think in one of the early Google paper, they had this really nice quote that says, failures are the norm rather than the exception. Okay, so servers crash, storage nodes crash, compute nodes crash. Sometimes if they crash, they recover. Sometimes they don't recover and you lose the data that was on the disk. So these failures happen, but also other types of failures happen, which I think will not happen to us during this talk today, is that processes become unresponsive, that we have network disconnection. For example, sometimes servers can become slow because they're busy doing garbage collection stalls, and sometimes the network can be overflowing and drop messages and be asynchronous and causes communication problems. Sometimes networks go down for periods and you can't connect for a while. So all of these problems are going to happen. And if you're going to start storing files in the cloud, you're going to have to take them into consideration and design a solution that will preserve the data consistent and persistent and hopefully also available as much as possible. So just to back up what I said on the previous slide, again, a quick search on the internet, and you can see that all kinds of companies are reporting anecdotal evidence about their failures. Microsoft, they have a very big network. They say they have about 40 link failures a day. These failures can be 5 minutes to a week long. Google reported in every cluster's first year, 5 racks see 50% packet loss, and a lot of work lost on maintenance, on router failures, and companies that actually had more serious failures because their systems were not designed to work correctly despite the failures. There were some famous ones, kind of split brain scenarios in Netflix, in GitHub, in AWS, scenarios where actually the data became corrupted and became inconsistent because the system was not designed to work correctly despite asynchronous communication failures. So hopefully this little small sample of anecdotes will convince you that indeed this is really important to take this into account when designing a real system. That we really do have to worry about failures, about server failures, about network failures, about asynchronous communication, and so on. And that's kind of the motivation for everything we're going to talk about today. So in terms of making the bridge from practice to theory, I would say in theory we call all of this asynchrony. So basically, if you look at a model for distributed computing, you can think of a synchronous model where communication delays are bounded and computation times are bounded, and you can look at the asynchronous model, which is what we're talking about today, where the network delays are not bounded and the computation times are not bounded. And this captures all these errors that we get because networks are dropping packets, so we don't know how long it's going to take us to communicate with another party, and all kinds of garbage collection stalls and things like that. So in an asynchronous system, the important thing to understand is the first bullet here, is that an unresponsive node cannot be distinguished from a crashed one. So sometimes you try to connect to a server, you can't really know if the server is there and you're not hearing from it because of communication problems, because of asynchrony, or the server has crashed, in which case you probably would want to use a backup server instead. And this is the root of these split brain behaviors that I mentioned, for example, in GitHub. There was some false detection, okay, false suspicion. Somebody thought, not somebody, I mean, some software thought that the server has crashed while it didn't crash. And then there was a backup server working, but the primary was also still alive. This is the challenge of working with asynchrony. That's the model we look at today. So this is the formal model slide. I tried to put it in a picture so it won't look too scary, but this is the theoretical model that we consider. So we consider a system where we have n n servers, and in this example you see 4 drawn here, but n can be 3, it could be 5, it could be 7, it could be whatever you want. And it's the threshold failure model where some threshold f of the servers may fail, but not more of them. So, for example, we have 3 servers and we want to tolerate 1 failure, then n equals 3 and f equals 1. And in this talk, I'm going to talk only about crash failures. So if the server fails, it crashes and that's it. And it doesn't become malicious or behave in a Byzantine way. I understand that tomorrow you have a talk by Rodriguez, who's going to basically extend what we're doing now to the Byzantine case. But for today, we're only talking about crash failures. And then we have asynchronous communication. And at the top, you see all these little laptops. These are the clients. These are the people who have their files stored in the cloud, and they want to talk to the servers in the cloud. Their communication is completely asynchronous. Actually, the servers are also not able to synchronously communicate with each other. And actually, in this talk, we look at solutions where the servers actually don't even talk to each other. All the communication is through clients. But even if they do talk to each other, it's only asynchronous. And clients are less reliable than servers, because if a user is trying to connect to his Dropbox account from his cell phone, then it's very likely that the cell phone will disconnect. We're not assuming that the majority of them are going to be correct, so we don't have a limit on the number of failures of clients. Clients can always fail at any time. For the servers, yes, we have a restriction. We try to be reliable. We built a data center. We put there 5 servers. We hope no more than 2 of them will crash. For the clients that connect to the service, you can have 1,000 clients and they can all fail as much as they want. So this is the model, and I hope we're all on the same page and this is understood. But if anybody has any questions about the assumptions or the model, please do ask them on the Discord channel, and Ivan is going to forward the question to me. I'm not going to stop to wait for this, but it's okay if you interrupt me with a question in a few seconds. I will just, again, if there are any questions about what we're assuming here or what the model is, please ask them, because it's important that we'll all be on the same page. So we're trying to achieve fault tolerance. We know that F servers are going to fail. What are we going to do? So fault tolerance 101, the basic thing you do if there's something you don't want to lose is you keep multiple copies of it, right? Replication. So for example, we're going to take every data item and keep 3 copies of it. And we're going to put them on different storage nodes. And if we want to also have some kind of disaster recovery or to recover failures of entire data centers, then we can put them in different data centers. Or if we just want to tolerate rack failures, we put them in different racks in the same data center. If we just want to tolerate individual storage node or disk failures, we can put them together in the same rack. We can decide what kind of diversity we want, depending on what kind of failure we want to tolerate. But that's the basics of what we're going to try to do. We're going to keep multiple replicas, and actually most storage systems use this approach. Things like HDFS would keep 3 copies of your file typically, and so on. So, Ivan, do you have any questions?
No, so far we are good. No questions so far.
Okay. Okay, thank you. So now I have a question for you. We'll see. The question is, now we've established our model. The model is that we have clients and we have servers and we have failures, and the system is asynchronous. And can we provide the illusion of reliable storage this way that is consistent, that has like atomic access guarantees? Can we do that? That's kind of a question. Maybe we can take a poll on the on the Discord channel and see what people think about this. Is it Discord or Telegram? I'm not sure.
So just please write yes or no whenever you have an opinion on that question.
Yeah. And you can write also the reason and why yes or why no, what you think. So Ivan, is it Discord or Telegram?
The chat is on the Telegram, so I see somebody is typing the answers, so I believe we can come up with a suggestion in a few moments. But that was not the answer to your question, that was the question in response. So the question is to clarify if we are talking about this illusion only in the synchronous setting, or we do consider partially synchronous setting, or we do consider only asynchronous settings.
This is a good question. So far I'm only talking about completely asynchronous setting. We just have completely asynchronous, we don't have partial synchrony, we don't have eventual synchrony, no guarantees on synchrony at all. And we want to provide the illusion of consistent storage to clients that are asynchronous, that access it asynchronously.
Okay, so we have a few answers. So the first answer is saying no, we cannot provide the illusion of reliable atomic shared memory because the consensus is unreachable. And the student who asked the question about the asynchrony is saying that no, that we cannot provide the illusion.
Okay, so now I have to confess that even though you asked for a clarification, the question is still not well defined, because I said reliable atomic shared memory, but I didn't say what kind of shared memory objects. And it really depends on that. And the two people who answered have heard of the, probably more people who haven't answered, also among the audience, have heard of the famous FLP result by Fisher, Leach, and Patterson, which shows that it is not possible to solve consensus in an asynchronous message passing system. So if the type of reliable shared memory that we want requires consensus, then the answer is no. But what I'm going to show today, which might surprise you, is that if we want a weaker type of shared memory that is not as strong as consensus, we actually can do it in an asynchronous message passing system. So that's what I'm going to move on to show now.
Edith,
so,
before we continue,
yes.
may I suggest maybe say a few words to clarify the relation of this topic to the CAP theorem, which is consistency, availability, and partition tolerance, because there is a reference to the theorem inside the discussion room.
Okay, so that's another good question. And the CAP theorem also says that we can't. So there are a lot of things that we can't do. We have to be very precise about what we can or cannot do. The CIP theorem says that if you want consistency, which is something we're going to want here, that's what I mean by atomic, and you want partition tolerance, which means basically that you tolerate asynchrony because you cannot tell the difference between a partition and servers being slow. So partition tolerance and asynchrony are actually the same. Then you cannot have the A of CAP, the availability. Maybe I'll use my pen to write this. See if this works, right? So here. C. Whoops. It's not working? Yeah. No. Sorry. C A P. Okay, so the C of the CAP is consistency. And we want that. So that's the atomic part. That's more. Whoops. Where did my presentation go? Do you see my presentation?
No, we actually currently see your desktop with a lovely picture in the background.
Yes, it disappeared. What happened? Okay, sorry for that. I don't know what happened. Just a second. I was trying to draw a picture. Sorry for the technical trouble. I don't know. Yes, yes. The PowerPoint is open. It just kind of the display disappeared. Let me try to share it. Let's try again. You share. Okay, is that fine? You see it now?
Yes, now we can see the
Yes,
slides
now.
back.
Okay. Okay. Sorry for that. So anyway, this is the Cip theorem. Maybe you've heard about it. It says you can't have. Whoops. Sorry. C. C. Whoops. No. I'm going to do one more attempt at this. No. Okay, I'm going to skip writing on the screen because it's not working for me. But so the CIP theorem says you look at three things: consistency, availability, and partition tolerance. And you can't have all three of them. So the C is the atomic here. We want that. And the P is the asynchrony. The partition tolerance is the same as asynchrony. But the A is the availability is the one that we're going to give up here, actually. We're going to have reduced availability. We're not going to offer availability to clients that are partitioned from their servers. So that's why we're going to be able to solve this problem. I hope that answers the question. Yes,
Yeah,
Ivan?
I believe that's good. We can continue.
Okay.
Yeah.
Okay, so sorry for the technical problems, but okay. So what we're going to what we're going to ask, the question we're going to ask is, can we do an emulation of shared memory in this system where we have servers, the servers on the bottom, we have n servers, and any f of them can crash. And then we're going to have a protocol. This is the share successful? I don't know what's going on. Okay, sorry. Maybe I'll try this again. Okay, this box here. Yeah, now it can work. Now it works. Okay, this box here, this is in the middle, the blue one. That's the reliable register emulation. That's the protocol we're going to run. And this protocol is going to allow the clients to access the registers, the servers, the shared memory, as if it's a shared to all of them. All the clients have some shared memory abstraction. They're all going to be able to access it, and the protocol is going to run between them and between the servers. So this is what we want to implement. We want to implement something called a register, which is simpler than general purpose shared memory and doesn't require consensus. And a register is, I know most people, when I say to them register, they think of a machine architecture and this thing that's in the CPU, but in distributed algorithms jargon, actually introduced by Leslie Lamport, a register is just a memory location that holds a value and can be read and written, and it doesn't offer any more sophisticated type of access. Okay, so its interface is only read and write. Okay, not more than that.
Idit?
Yes.
Idit? Just to clarify,
yes.
Currently we see the slide with emulating shared memory title with no drawings. So just to synchronize that we are on the same
so
track,
we have a problem here.
we do currently see the slide.
Okay, so that's not what I'm seeing. Okay. Sorry for the technical problems. Let me try this again. Now you don't see anything, right?
Yes, we do see the web camera view.
Just the camera, okay. And now I'm going. Okay, but now you see the slides? Okay, okay, good. So this is a register. A register is just an object, a shared memory object, whose only interface is read and write. Okay, we can't do atomic read, modify, write, compare and swap operations. We can't do them, just read and write. And we want the register to be atomic or linearizable. And I assume most of you know what linearizability means, but just in case some people don't, I'm just going to go over it really quickly. So the idea of linearizability is that even though we have concurrent access to this object, it looks as if it's done sequentially. So basically, even if multiple processes are accessing simultaneously, one is reading and one is writing, for example, each operation can be sort of shrinked to an instant in time and just occur at some point, so they will occur in some order. This is not clear. Here is an example. Here we have this is a space-time diagram. The x-axis is time, and the y-axis is the processes or the threads. So we have here time moving from left to right, and we have the blue thread writing 0 and the red thread writing 1 at the same time. They both invoke their operations. So these are threads or processes or clients writing to their storage. They both invoke their operation at the same time. And at some point later, the red thread finishes writing and reads 0. And the question is this linearizable? Okay. So try to think about it for a minute. Does it seem to you like this is a correct execution or not? Is it a linearizable one? And now I hope you
suggest we
all
can
wish
have
to.
a poll.
Yes. I think it will take a long time to take a poll, or you already have.
Yeah. So let's repeat the poll once again. Just drop the line to the chat room if you believe that this particular execution is linearizable or not, and any commentary why, yes or no. So yeah, the majority of votes saying that this execution is linearizable.
Yes, so indeed it is linearizable because it is possible to let me try this again if it works. It's possible to order the right one here. Yes, it works. And the right 0 here. Okay, because this is, we can shrink the right one to this point and the right 0 to this point. And then the right one happens first, then the right 0, and then the read 0 happens, and everything is in order. So indeed, this one is linearizable. Okay, let's continue. What about this one? What about this example? Is this linearizable? If the blue thread now starts to read and it reads 1, is this linearizable?
Same question. Please post your answers to the Telegram chat room. And as a side note, one attendee of today's talk is also provided a valid explanation why the previous slide, the example one, was the linearizable execution, basically repeating your argument that we can make two writes ordered in a particular fashion. And getting back to the current question regarding the example number 2, there is a consensus inside the chat room that this execution is not linearizable.
Okay, so that's very good. So I see that that people understand the concept of linearizability, which is very good. So the reason this is not linearizable is because we have to preserve the order within each process, and the blue process read 1 after writing 0, and because it reads 1 after writing 0, it means that the write 1 must have happened in the middle between the write 0 and the read 1, and therefore when it's over, the value cannot be 0. So this is indeed not linearizable. Okay, so that's the safety requirement that we want for a register. We want it to be linearizable. We want to support read and write to be linearizable. And we also want something called wait freedom, which means that every operation by a correct process eventually completes in a finite number of the process's steps. So we have liveness for all operations. Now, you pointed out in the Telegram channel that indeed the Cip Theorem says we can't have progress for clients if they're disconnected from the servers. So for the sake of this presentation, we're not going to allow partitions to last forever. So we're going to allow asynchrony, but not partitions forever. So eventually, the communication will be repaired and the client will be able to contact some servers. But we don't know how long it's going to take. And we want to ensure that if the client eventually succeeds to talk to the correct servers, F servers can fail, but it can talk to the other N minus F. It's not partitioned from them, then it will be able to complete the read or write operation. So now I can make the question more accurate. Before I asked you, can we provide the illusion of shared memory? What is illusion? What is shared memory? Now the question is well defined. Can we emulate a wait-free atomic shared register in an asynchronous system where clients and servers can fail? So again, the rules of the game here. There are no partitions that are permanent. All the communication is asynchronous, but eventually you manage to communicate. The clients eventually manage to communicate with all the correct servers, not with the faulty ones. If they don't communicate with the server, they don't know if the server is faulty or slow. So that's the asynchronous model, but we're trying to emulate only a register. We're not trying to solve consensus. If we wanted to solve consensus, as you correctly pointed out, FLP would say it's impossible. But we're only going to try to emulate a register. And actually, we can do that. And that's what I'm going to show you in a little while. So first of all, let's try to think what we would do if we didn't have to tolerate failures. Just as a thought, as a preliminary to answering. So the question we want to answer is this one: do we do it in a faulty scenario? But if we didn't have faults, what would we do? Well, if we didn't have failures or no server failures, but clients can still fail, then we could have each server keep a local copy of the register, which is replicated in all the servers, and then the only thing we would have to worry about is the consistency of all these copies. So how can we ensure consistency of all the copies in this case if we know there are no failures? Any suggestions, maybe?
If you have any suggestions, just please post them to the chat. In the meanwhile, while we are collecting any suggestions here, so Idit, could you please clarify, shall we pursue the asynchronous or model of communication, or shall we explain a little bit more in detail how the partition tolerance is connected to the asynchrony? Because there is a couple of questions on that matter in the Telegram chat. And I wonder if you would like to cover this question right now, or we shall postpone it to the discussion room. So what's your suggestion?
Actually, I'll cover it right now. I'm sorry, because maybe this wasn't clear because it wasn't in my slides. So I was kind of, but I do want to respond to that. So in the asynchronous communication, what we assume is that eventually the partition is repaired. Okay, so but basically we're saying yes, it's possible for the network to partition. So you send a message to a server and it might not respond for 5 minutes, which is a very long time, but then after 5 minutes maybe the partition will be repaired and we will get a response from the server. We'll manage to communicate to them. The Cip theorem says that while you have partitions, you don't have availability. So you can think of it as that while the partition is ongoing, the clients don't have any availability. They don't get response from their servers, so they can't have their service available. If you want the clients to have availability while they're partitioned from the server, by the Cip theorem, you have to forgo consistency. Okay, so we're not going to forgo consistency. So we're not going to provide availability while there are partitions. We're going only to provide availability after the partitions are repaired. This is going to be the way we manage the Cip trade-off. So we look at the asynchronous model, and the wait freedom, the availability, the liveness guarantee is after the partitions are repaired. There's no
And
availability.
one more question.
Yes.
One more question on the same matter. Is it valid
Yes.
to say if the partitions are not permanent, if they are time-bounded,
Yes.
is it correct to say that system is partially asynchronous in that case?
The partitions are not, yes, that's another good question because it's an important distinction. The partitions are not time-bounded, but they are finite. So we don't have a bound on how long they take. We just know that eventually they complete. I know this is really confusing, but the big difference between the eventual synchrony or the partial synchrony, as it's sometimes called, model and the asynchronous model is that in partial synchrony, we have a bound on how long things take. In the asynchronous model, we know they eventually happen, so they do take finite time, but we don't have bound on this finite time. It's finite, but it's unbounded. So you send a message, there is no bound how long it takes. There are, for every natural number then you could think of, you could say, does it take 7 seconds? It could take 8. Does it take 8 seconds? It could take 9. But eventually it's going to get there. So that's kind of a little fine-grained distinction.
Thanks for the explanation. It seems that it's clear right now how to distinguish a synchronous case and the partially synchronous case. And a little bit more, it's now a bit more clear what exactly the FLP theorem says about the asynchronous setting. And getting back to the failure-free case of the registers, there is a suggestion inside the chat. I'm not sure if I'm correct in voicing the suggestion, but it says like we can use shared memory and copies in validation techniques to achieve the desired register construction. I'm not sure if that makes any suggestions for you how to proceed here.
I think it's
and
a little
to
vague.
continue,
yes.
Maybe. And yet another suggestion here is to model register inside 2 steps. First, lock all the replicas of the register, then write the new value in all the replicas and release the lock.
Yeah. Yes, so that's a good answer. So locking it is one option, and writing in all the copies is another option. And what people often use in this case is primary backup, where we have one copy that we write to, and this copy sends updates to the other replicas, and they're consistent. You can do a general, once you don't allow failures, then FLP is not relevant anymore. You can solve consensus. FLP only says that if there are failures, you can solve consensus. So you could just do state machine replication. You can use some kind of an atomic broadcast service that delivers messages in the same order at all the servers. This can be done, for example, by having one server broadcast be the leader, and everybody sends the message to the leader, and the leader sends it to everybody, and everybody gets it in the order that the leader decides to do it. And the leader is not going to fail because we don't have failures, so we don't have a problem, right? The problem arises when there are failures, and then the leader fails and we need to replace it with another leader, but because we're in an asynchronous system, we don't know if the leader actually failed or not. So that's going to work. And here's what it might look like. So for example, if we had some kind of an atomic broadcast service, then we could just, whenever we have a client request, we could broadcast it using the service. For example, send it to the leader and let the leader decide on its order and send it to everybody else. When we deliver the message that we got it from the leader, then we are going to, if it's a write it to the local copy. If it's a read, send a response to the client. And it's fairly easy to see that this protocol is linearizable, okay? Because all the copies are applying the updates in the same order and they're applying the reads in the same order. It's fairly easy to see that this actually works. So if we don't have problems, we don't have failures, we don't have a problem. Okay, but let's go back now to the problem we're actually trying to solve. What happens if processes can crash? Does it work? Well, as you pointed out earlier, it doesn't work because FLP says you cannot do it. You cannot do consensus or atomic broadcast or state machine replication in an asynchronous network with crash failures. And what many of you pointed out also is that if you have eventual synchrony or partial synchrony, as it's sometimes called, or failure detectors, then you could do something like Paxos or Zookeeper or Raft and solve consensus. But this is not our model right now. Right now, we are assuming the FLP model. So let me show you what you can still do despite of FLP if we're just trying to do a register. So let's look at a simple case first, and then we'll generalize it later, where we have one reader and one writer. So we have two processes. One of them wants to be able to write to the register, and one of them wants to be able to read from the register, okay? And we're going to have as many servers as we want for the fault tolerance, because we know some can fail. And to make things a little simpler right now for the discussion, we're going to forget that we have clients and servers. We're just going to have processes, okay? So the same process can do the read and write on its own, so it can be the client, and it can also help maintain the state, so it can be the server. Just so it's easier to think about the protocol, later we can separate them again, the clients and the servers. So what would be a trivial way to do it, okay? If I told you, okay, you have processes, one of them needs to be able to read, one of them needs to be able to write, how do you share the information between them? How do you allow one of them to write and the other one to read what the first one wrote? So I'm not going to do a poll now because I'm going to do one in a minute and I want to do one every second, but I assume many of you would come up with this really simple solution where, okay, so the writer wants to write, they just send a message to the reader. And then when the reader wants to read, it just reads the latest value that it got from the writer. If anybody wants to propose an alternative solution, that's fine too. But I want to ask now if you see any issues with this trivial solution, and take a poll a little bit and see if anybody sees an issue with this solution.
So any alternative suggestions, please type them to the chat room.
Yeah, or issues with this solution. Problems that you, or questions that arise.
The chat room is currently quite silent, so maybe I shall voice one of the objections why what may go wrong here. Let's say if we're talking about the case when there are failures, what happens if the message is not delivered, for example?
Yes. So we're assuming that the messages are eventually delivered if both the reader and the writer are correct. But the message might be not delivered if, for example, the writer fails. But if the writer fails, then the write doesn't have to complete. So that is fine. And the message might not be delivered if the reader fails. But if the reader fails, then it doesn't need to read. So that's fine too. So that seems like it should work, right? If we know that if both are correct, then the writer sends the message to the reader, then both the writer can write and the reader can read. But still...
Okay, one more objection might be how we can
yes.
prove linear usability here.
Yes, that's a very good point. And to pinpoint it a little more, let me ask another question. I said the writer sends the message to the reader, but when does the operation complete? When we talk about linear usability, we talk about the execution interval of the operation. So we say, if the read overlaps a write, the read must, whatever. We define the execution. What is the execution interval of the write? When does the write complete? Does the writer return the ACK when it sends the message or not? Does anybody see a problem now, maybe?
Maybe, and on a side note, could you please clarify if we do consider reorderings between the messages in our model right now?
Yeah, so let's assume we don't have reorderings because reorderings are easy to solve with sequence numbers, so we can not worry about them right now. So whenever we want to do a write, the writer sends a message to the reader and says, this is the new value. When can the writer return an ACK and say to the client, I've finished the write? The write is over, it's complete.
So I believe two major options here are to return immediately or to return upon receiving the acknowledgement.
An acknowledgement from the reader, right? So there's nothing on the telephone? Yes?
Yeah, the chat room is quite quiet right now, so maybe we can continue explaining the details here.
Fine. Yes, okay, so maybe you see this, but the challenge is this, right? If the writer, as you pointed out, Evan, if the writer will immediately return, that's one option. It will send a message and then return. Then we're going to violate linear usability because the message might take an arbitrarily long time to get to the reader. And meanwhile, the write is complete, right? The execution interval, we'll take another attempt at annotating, right? But if we have the execution interval of the read, the write, this is the write, and this is the read. But the message is only going to be delivered here, okay? It's going to send a message, return an ACK. Now a read is going to happen. It's going to read the old value, and only here the message will arrive. I don't know how my drawing is, but is it clear, the problem? Or maybe I should clarify it again.
Once again.
Yes, if it's clear.
So in the meanwhile, we have a preliminary feedback that the problem here is clear. So we can continue, I suggest.
Okay. Okay, that's fine. Clear? I don't know. Why is this not going away? Clear all blanks. I don't know why it's not going away. Okay, so It seems like I used a different software to annotate this. Sorry for the technical problems. So the thing is that if the writer simply sends a message to the reader and returns an ACK right away, we're going to violate linearizability. And if it wants to wait for an ACK, then the writer will, yes. Okay, sorry. Yeah, but can you help me remove this drawings? I don't know. These are not annotations from the. I don't know how to remove them. I don't know. Okay, never mind. Okay, let me try to sort this out later. Let me continue. So the problem we have is that if the reader if the reader if the writer is going to have to send in a message to the reader and wait for the reader to respond, then the write is not going to be wait free, because the reader might fail, and then the write will not be able to respond on its own. Okay, so I hope that's clear. But I can't. Excuse me, just a minute, okay? Okay. I'm sorry, really, but I have some problems
Yes, so
with this.
while we're
Yes,
handling the technical issues, I can provide you with like preliminary feedback. So the chat room says
yes,
that the concepts described so far are quite clear. So I believe we can continue with just like a few more steps, like just a little bit
okay,
faster. It seems that the material is
okay,
going on quite good.
Okay, yeah.
okay, good.
I just told to fill a small pause that you have here. So I honestly I don't know what task, because it seems that everything should be clear. If anybody have questions, please ask. Like what do you think of the first part, Ivan? What did you get something new yet, or
Uh, I believe it's worthwhile to recap what was happening in the first
yeah,
part. So
let's
we
probably
did
recap.
introduce we did introduce the problem that we would like to build a distributed storage which is resilient to the failures. So we are actually trying to capture the essence of distributed storage by introducing the register interface, which is just like an object with a simple read-write methods, so they could be called independently. We did a quick recap on the notion of linearizability, and now we're trying to build a wait-free register in the distributed setting that would satisfy our end goal of building the very basic unitary storage of the data. Idit, is that the correct recap of what this
Yeah,
happened?
great, wonderful recap. Thank you very much.
Okay, let's continue then.
Let's continue. Okay, so I've shared my slides. Can you see them now? Yes. Okay, so
Yeah, it's good.
let's get to the real solution. Again, we're starting with a single reader and a single writer, but we'll build up to multiple readers and writers afterwards. So this protocol tolerates failures of any minority of the processes. So if we have 3 processes, we can tolerate 1 failure. If we have 5 processes, we can tolerate 2 failures. Basically, this is optimal for asynchronous systems, but I'm not going to show that now. And The main idea of the protocol is to store the value that we want to write at the majority of the processes before the write completes. So the write can complete and return an acknowledgement after it's written to a majority, to read from a majority, and because every two sets that include a majority intersect, every read will see the latest written value and will be able to satisfy linearizability. So this is our an example. We have, in this example, n is 5 and f is 2, and two servers can fail. And the writer wants to write this green block, and it writes it to 3 of the servers. Now, maybe the writer would want to write it to all 5 of the servers, but because only 3 responded with X, and the writer doesn't know if the other 2 are correct or faulty, it can't continue to wait for them forever, because it cannot distinguish the case that they're correct or faulty, because F can fail. So as far as it can tell, they might be faulty, so it returns. It writes to n minus f, which is a majority, but it can't wait for more servers and write to more. So it goes away. Now, 2 of these servers that it wrote to crash. This is allowed because we tolerate F failures. F is 2 in this case, so 2 servers crash. Reader comes along. It also reads from a majority, which is 3 servers. No problem, right? It finds the green value because every 2 majorities intersect, it can return a correct value. So no problem, everything is good. Now the writer, these servers actually didn't really crash. They were just slow. The reader thought they crashed, but they're still there and they're still holding the green value. Now the writer wants to write the orange value. And again, it writes to a majority, but this time these 2 servers on the left, they're very slow. So the writer doesn't manage to write to them. And again, it can't wait for more than n minus f responses because they might have been faulty. So it returns and leaves the storage in this situation with 3 orange copies and 2 green copies. Now comes along the reader, and it also reads from a majority, and it can't wait for more. So it reads from n minus f servers, and it reads 1 green copy and 1 orange copy. So what can it do now? Which one can it return? By linearizability, it's supposed to return the orange copy because that's the latest write that completed. If it would take a majority vote, then it would return the green copy because it got 2 greens and 1 orange. So it can't really take a majority vote. It needs to somehow recognize that the orange copy is more up to date. And I'm not going to stop here for another poll, let me just continue. Probably most of you can guess that we can solve this by timestamps, and it's right now it's really easy to use timestamps because we have one writer, okay? So the writer can just number, use version numbers or timestamps, can just number the writes. So when the writer will write the green value, it will tag it with the number 1. And when the writer will write the orange value, it will tag it with the number 2. And next time the writer will write, it will tag it with the number 3 and so on. And now the reader has no problem. It sees 2 green copies, but they both have the number 1, and it sees 1 orange copy and it has the number 2, and it knows that it can just return the orange one and everything is fine. So that was a graphical illustration. Let me write the pseudocode of the algorithm. So basically, at each process, we keep a copy of the register, right? We have copies at all the processes. And we have a tag, which is the timestamp. It's initially 0. That's the timestamp of the latest write. And to write, what you do is you find a bigger number than before, because we have one writer, it could just increment the previous number that it used. Write the value to the local copy, write the tag to the local tag, and then send the write message to all the other processes. And every process that receives this message check that it's new, and if yes, it sets the value message and the tag to the tag and sends an acknowledgement to the writer. Now it should be clear when the write can complete, right? As we talked before, the write can wait for an acknowledgement from a majority, and because we don't distinguish clients from servers here, so it's also the client and the server, so it counts in the acknowledgement from itself too, and returns the acknowledgement to its client. Okay, I hope this is clear. Oops, right. How does the read work? Well, the read, again, as we said, is read from a majority. So we're going to send the read message to all the nodes, send an acknowledgement, and every process that receives this read sends the value X, that's the value of the register, and T, that's the timestamp to the reader. And when the reader receives this message from a majority, it just chooses the value associated with the biggest value and stores these in its local copy and returns it. So, Ivan, you think the algorithm is clear? Should we wait for questions? Or?
I believe we can post the questions in a synchronous manner as we are in the distributed computing school. So if somebody have any questions in the meanwhile, please post them to the chat room. But given the current feedback, I would say that this material is quite clear for the students, so we can continue, and I will give you an update if somebody comes up with a question.
Okay, so let's continue. So the question is this correct? Well, obviously it is, but let me try to convince you that we get the linearizability semantics here. So the observation here that the only possible overlap between operations is between a read and a write, okay? There's no possible for two reads to overlap, and there's no possible for two writes to overlap. And the reason for this is because, quite prosaic, is because we only consider the case of a single reader and a single writer, and each process has one operation ongoing at a time. So we have at most one read going on at a time, and at most one write going on at a time, so we don't have to worry about them. We only have to worry about overlap between a read and a write. So for linearizability, we need the following. We need to be sure that if the read does not overlap any write, it reads the value of the last write. How do we ensure that? Well, we observe that the read reads at least one copy that was written by the last write. And that follows from the fact that the writer writes to a majority and the reader reads to a majority, and two majorities intersect. And this copy that it reads, it has the highest tag, it has the highest timestamp. And that's simply because the timestamps are monotonically increasing. So it's very obvious that the read that doesn't overlap any write will return the value of the last write. Now, we come to the more tricky question is what is the order when there is an overlap between the read and the write? So some copies may be updated, but less than the majority, and the reader might read some copy with the old value, some copy with the new value. Maybe it will miss the new value altogether. So in this case, the linearization, the order between the read and the write is going to be based on the timestamp. If the reader sees the timestamp of the write, it returns the value associated with that timestamp, then the read is going to be after the write. And if the reader doesn't find any of the copies written by the write and it returns an operation with the smaller timestamp, then it's going to be before the write. But we have to consider this. We know that the only overlap is between the read and the write, but we can have two reads overlapping the same write. So we can have this scenario, for example. We can have a write ongoing, it's taking a very long time. And then we have one read, which is complete, and then another read starts. What is going to happen if the write is so far managed to write one copy, not a majority? And the first read that happens is going to find this exact one copy that was written. But the second read, it reads a different majority and doesn't find that copy. That copy, okay, I'm not sure. Try to explain it again. Let's say we have 3 servers. The write manages to write to one of them before the first read. And the first read reads this one server. But the second read only reads the 2 other servers, and they're not up to date yet. In this case, we might fear that the second read will return the old value after the previous read has returned the new value, and this will break linearizability. So maybe we can get some feedback on whether the problem is clear, and if people see whether this breaks linearizability, whether the solution is correct after all or not, and if it's correct, why it's correct.
Yeah, the people are currently saying that this system is not linearizable. So in this algorithm in particular, you cannot achieve a linearizable execution given this particular example with 2 reads.
So this example suggests that it's not linearizable, right?
Yes.
Okay, it seems like that, but actually that's not true. And I'll tell you why. It's not true. And I'll go back to the algorithm and I'll show you. It was hidden in the algorithm and nobody noticed when I went through this. But if you look at the penultimate line here, it says, when the reader receives an acknowledgement, it always stores the values in its local copy. Okay? We have one reader. When the reader reads a value, it stores it in the local copy. Okay, so if we go back to this example, it's not possible for the read not to find any copy because it always reads its own copy. It's one of the processes. And in the first read, once it found the value, the new value, the one with its timestamp, it stored it locally. And now it's not possible for it to read a set of values that doesn't include this copy because it already copied it to its own local register. Okay, is that clear now? Maybe. So it is linearizable actually. Is it clear? I can go back to...
Yeah, there is just one small confusion. Could you please show the slide with 2 reads concurrent to the right with the linearization diagram? Yeah, this one.
Yes.
So there was just a bit confusion. What would happen if those 2 reads happen on 2 different readers? So that's not really clear.
Yes, that's an excellent question because it doesn't work, right? But we're getting to that. So that's an excellent question because indeed this works only because we consider it a single reader. But now the next thing we're going to do, and somebody who wrote this has kind of anticipated the future, we're going to move to the multiple reader case. We're going to have to find a different solution for this problem. But let me just, before that, say that right now we do have linearizability because we have a single reader. And we also have wait freedom because the only time we wait is for a majority of responses, and there is a correct majority. And here I want to go back to the algorithm again and point out something. And you see, upon receive a write, the second bullet, the first sub-bullet, if it's new, then we update it. But in any case, we send an ACK, okay? You can see that the ACK is being sent in any case, even if the tag is not new. So this is important. Even if we are not accepting the message, we have to send an ACK. So what happened? Why is it not disappearing now? I'm going to figure this out by the end of the talk. Okay. Okay, so now we're going to talk about the multi-reader case, and all the processes can read. And asking here, does the previous solution work? But somebody already beat me to the chase and answered the questions and said, what if two reads by different processes overlap the same write? Right? And here we have exactly this problem. The first read is going to find a copy that was written. The second read, it's a different process. It might hit a different majority and not find a copy that was written, and it would violate linearizability. Okay? So the same solution doesn't work. And we're going to have to use a technique that is called write back. We're going to have to go back and write the value that we read to ensure that not only reads by the same process will see it, but also that reads by other processes will see it. So when the reader receives a message, a redact message, it doesn't return. Okay, the first two lines in the pseudocode are the same as before. It chooses the value and stores it locally, but in the single reader case, the next line said return. Here we don't return. We send a propagate message to everybody. And propagate is treated exactly like a write. This is exactly what we do on a write. If it's new, we update the register, and in any case, whether we update it or not, we send an ACK. This is exactly what we did on write. And then we wait for majority to send these acknowledgements and to return it. Okay, so this is what it looks like. We do the read, we find the value to return. We know what we're going to return, but we can't go home yet because we have to make sure that the future reads will see the same value. So we propagate it. We wait for it to be propagated to a majority, and only then we return. Okay? So that's the multi-reader case. Now we're going to extend it to multiple writers. And again, the question is, why do we need to do anything special? Why doesn't the previous solution work? What do we need to do in order to tolerate multiple writers? What do we need to change and why?
So I believe it's worthwhile to cover a little bit in more detail what exactly happens inside the write operation when we do assign the timestamp when we write. How do we get the new tag, the new?
Yeah, exactly. So the algorithm so far, the timestamp was just a monotonically increasing counter. So if I wrote 7, I will write 8 now. But obviously that doesn't work. Because if I wrote 7 and then meanwhile you wrote 8 and 9 and 10 and 11 and I'm going to write 8 now, then it's going to be ignored, right? All the processes are going to see that it's an old tag and ignore it. So I do need to get a higher timestamp than all the previous writes. And this is what we need to do. So first thing, we need to ensure the copies always overwrite the value if it's fresh, if it has a newer tag. So we have to make sure that the different writers use different tags, because if two writers are going to use the same tag, then we're going to have a mess. We're going to have some copies that think that version 8 is one value, and some copies think that version 8 is a different value. How can we ensure that?
Idit,
Yes.
just
Yes.
Sorry to interrupt you. Just before we jump inside this particular detail, there is one more question came regarding the multi-reader construction. So could you please elaborate in a little bit more detail what would happen if two reads are happening concurrently, these two reads with the write-back operation? What if those two read operations happening concurrently? Why we can ensure the linearizability?
Okay, so the reads are happening concurrently, and there are two options, right? Either they read the same value or they read the different values. If they read the same value, they're concurrent. If they read the same value, then I don't know which picture to show, maybe this one. Then here they will propagate the same value, okay? So if both of them saw version 7 and both of them propagate version 7, it's not a problem because every copy, every replica will see version 7 is the latest and will update it. And if it's already 7, it will ignore the message. So everything will be fine. If the reads see two different values, okay? For example, we have one reader that sees version 7 and one reader sees version 8. Then the first reader will propagate version 7, the second one will propagate version 8. Every copy that will hear from the second reader will update it to 8. If it hears the 8 after the 7, it will overwrite the 7 with the 8. If it hears only the 8 and not the 7, when it gets the message for the 7, it will ignore it because it always uses the latest one. So the later reader will manage to propagate the 8. But it will still return the 7. Why is this okay? Because it's overlapping. So it's going to be a linearizable history where we have two overlapping reads. One of them returns 7 and one of them returns 8. We know they both overlap a write of 8, so it's not a problem. It's allowed for them to return 7 and 8. It doesn't violate linearizability. Is that clear, or should I draw the example more carefully?
Yes, the feedback that the answer is clear. On my side, I may add that the implicit linearization happens when we do propagate the value to the other readers. So once the other readers are aware of the new value, then this is how we can ensure that subsequent reads will receive the new value.
Subsequent ones will, yes, but the ones that already finished their first phase, they're already linearized before that. So yes, you're right. So we kind of linearize when we propagate the value, we ensure that later reads will see it. But those that are concurrent, they might have seen the other one. Okay, so the point is about the writes is that we can't have, we have all these messages going around, but we have to ensure that everything that is tagged with version 7 is the same. So we're going to use here a trick that probably you saw before because it's used in lots of algorithms, like in the bakery algorithm and in Paxos and in lots of distributed algorithms, is to just break ties by process ID. So I know that the last version that I saw, the last timestamp tag I saw was 6, and I want to send 7. But Ivan also might have seen 6 and wants to send 7, so I will write 7 Idit, and he will write 7 Ivan. They're both in I, but still there is an order between them, and then D will be smaller than V, so he will win. Okay. So we will be able to break the ties between us. Okay. So if two writers use the same tag, we're going to break the ties by process ID. Okay, what if a later write is going to use a smaller tag than an earlier one? That's a real problem, right? If I write with the tag 7 and my write is complete and returned, I have to ensure that all future writes will not disappear. They will be able to overwrite my value, okay? We have to make sure that if I start a new write, I actually succeed to overwrite the previous ones. So I succeed to get a bigger tag than all the ones that were written before, that were linearized before. Okay? And for this reason, to do multiple reader and multiple writer, we have to extend the write. So the write now looks like this. Before we start writing, we do a query, which is basically a read. It's exactly the same as a read. We send a read to everybody. We wait, as you can guess, for a majority. Okay, everybody that receives the query answers only with their tag in this case and not with the value. We wait for a majority. And once we hear from a majority, we pick a tag that is bigger than the one that we wrote in majority. because we know that every write that is already returned, that is already completed, that is not overlapping our write, has already written to a majority, and every two majorities intersect, we are sure to find the tag of every completed write and to use a bigger tag, okay? And then we continue. It is possible for two writes by two different writers to choose tags that are not compatible, right? If I choose a tag and I choose 5 Idit and somebody else also sees 4 and chooses 5, somebody else, okay, that can happen. Only thing is ensured here is that once a write is completed, is returned an acknowledgement to the reader, then any other writer that begins now will choose a bigger tag. Okay, two concurrent writes, yes, one of them will choose a bigger tag, one of them will choose a smaller tag, one of them will win. Okay, which one will win? The one with the bigger tag is the one is going to stay in the register. So now the write is going to look exactly like the read. If you remember, the read started with a read phase, which determined the value the read was going to return. But here, the read phase determines the tag that the writer is going to use. And then it continues with the write phase, which in the read's case was a write back of the value that it read, and in the write's case is a write of a new value. So both the read and the write have the same structure. They do a read from a majority, and then they do a write to a majority. So that's the end of this protocol, and if there are any questions, I can answer them. And I guess this is sort of as a teaser for the second half of the talk is, okay, so we got registers. What if we want something more sophisticated? What if we want queues or stacks or counters or something more sophisticated than that? So maybe we stop now to take questions and also thoughts on this.
Yes, while we are collecting the questions, just to notify, we have 5 minutes remaining in the first half of today's talk. So while we're collecting the questions, maybe it's a good idea to recap what we have achieved during this hour and a half.
Okay, do you want me to summarize? So I think basically I tried to explain the model of an asynchronous system with failures and the problem of emulating shared storage which is atomic and write-free in this setting. And I've showed that even though we know that consensus is not solvable in this setting by FLP, if we want something that is just a register where we can read and write values, we can do it using a protocol called ABD for its authors, Atiyah, Barnoy, and Dolev, which is based on reading from a majority and writing from a majority. And in the general case, if we want to support atomic reads and writes with multiple readers and writers, then both reads and writes have to first read all the copies or a majority of copies and then write to a majority of copies. That's the general idea of the. And maybe I should point out that majority is just an example of the quorum. Some of you may have heard of quorum systems. So in general, we can have different quorums and we can have different asymmetric quorums. We can have bigger write quorums and smaller read quorums, or bigger read quorums and smaller write quorums. So as long as every read quorum overlaps every write quorum, the protocol is correct. What we need to ensure is that every read finds a copy of the latest write. That's why we have to ensure that every read quorum intersects every write quorum. So for simplicity, we just said majority.
Edith?
Yes.
Yeah, we have 2.5 minutes remaining and one extremely good question. So I'm not sure if we are able to make it in 2 minutes, but let's try. The question is how exactly we did work around the FLP theorem by building the weight-free atomic register here, which sustains the failures.
We worked around FLP theorem because we did not solve consensus. And in fact, there is a variant of FLP, which is called the shared memory variant of FLP. And it shows that if you have read-write registers, you cannot solve consensus. So if you have an asynchronous system with only read-write registers, you cannot solve consensus. And in fact, maybe some of you have heard of the memory hierarchy, the shared weight-free shared memory hierarchy of Maurice Hurley, where he ranks objects by their power to solve consensus. And read-write registers have it's called the consensus number 1. What does it mean, 1? It means that you can only solve consensus among one process. Basically, one process can agree with itself based on a read-write register. But you cannot solve consensus with read-write objects in a weight-free manner if there are failures. Okay, you need, if you are familiar with consensus algorithms that use shared memory, usually they would use a test and set or a compare and swap or some other atomic instructions, but registers are not strong enough to solve consensus by themselves. And that's actually basically the point of the question here is that we only emulated a read-write register. Okay, if we wanted to do a queue or a stack, we couldn't. Okay, actually counters we can do, but not ones that can be implemented atomically. So not every object can you emulate it.
It seems that the teaser that you showed us for the next part you already showed that it's not possible, right?
Oh,
yeah,
it's not possible in the asynchronous model, but we'll talk about it in the partial synchrony model.
Okay, I see.
Okay. Yeah, okay. So let's stop here. We have a break of half an hour. So let's get a coffee or something and see you back in 30 minutes. Thank you very much, Idit, for your presentation and explanations.
During the first part of the talk, we saw that we can consider a completely asynchronous system with failures of a minority, and to implement emulation of an atomic read-write register using servers that can fail. So it was pointed out that this is a system model, asynchronous with failures, where we cannot solve consensus or because of FLP, but we can implement the weaker object, which is just a register, read-write register, so we could emulate distributed storage in this way. And just to sort of emphasize this point here, ABD, the algorithm that we saw due to Atiyah, Barnoy, and Dolev, works even if the system is completely asynchronous. Okay, we don't have any eventual synchrony or partial synchrony or timeouts or anything, or failure detectors or anything like that. And in contrast, if we use consensus like Paxos or Raft or one of these protocols, then we know that there will be periods where we'll do some operations, no operations will be able to complete. There will be no progress in case we're going to have multiple leaders at the same time. And when we have eventually synchronous periods, then there will be progress. So here in the ABD, in the protocol that we saw, there is always progress. Even if multiple writers try to write concurrently, they don't have to wait until one of them is a leader, is the only leader. But if we have two writes that happen concurrently, then in some sense they both succeed. But because this is a read-write register, when you one write overwrites the other, so one of the writers would prevail and will overwrite the rights of the other one. And I have a question here, which, but I'll tell you the answer. The answer is that the write that will stay that will end up being the later one is the one that's going to end up with a higher timestamp. Okay, so they won't compete with each other, but one of them will win. This is because we implemented the register. We can overwrite values, and we cannot do more complicated read, modify, write, and things like that we could do with Paxos. What I'm going to do in the next part of the talk is talk about what happens if we do want consensus, if we do want some object that is stronger than a read-write register. And I'm going to discuss this problem in the context of shared memory. So we're going to have some shared memory that the processes share via protocol like ABD or something like that. And now they're trying to implement something with richer functionality than just a read-write register, and they can use a consensus protocol like this Paxos. And to simplify things, we can do consensus is universal. If I mentioned in the first half, in the first part of the talk, I mentioned Morris Hurley's consensus hierarchy. So in the consensus hierarchy paper, he also shows that consensus is universal in the sense that once you can solve consensus, you can solve any problem. Okay, and maybe a lot of you are probably familiar with blockchain protocols. Blockchain protocols, we solve consensus in order to decide on the next block to append to the ledger, and that's universal. We can implement any functionality this way. So we're going to see how we can implement consensus using shared memory and some extra assumptions, which we know we need because of FLP. So to simplify the problem, we're going to solve a one-shot consensus, just to agree one time on one value. In more generally, we would need to agree many times, so we want to do something like a ledger where we agree on a sequence of operations. But let's now think of the basic primitive, which is agreeing on one value. So a consensus object, okay, is basically a shared object that has one method, and the method is decide. So each client that wants to use the consensus submits a proposal. So for example, client I submits a proposal VI by calling the decide function here. The subscript I indicates that this is the decide function called by process I with the value VI. And then the other processes are going to invoke decide with other values. And in the end, decide will return, and it will return some value DI to process I in a way that satisfies the three properties of consensus. So the three properties of consensus are agreement, meaning that all the processes decide on the same value, validity, which is kind of a non-triviality property that says that the decide has to be the value that somebody proposed, so it can't just make up its own. The consensus protocol can't just make up its own value. It has to choose one of the values proposed by one of the processes. And the liveness property is just termination, or you can think of it as wait freedom, meaning when you call the operation, it returns independently of other processes. Okay. So this is taking the classical message passing problem that you might be familiar with as consensus and framing it in the shared memory setting where we have an object that has one method and we invoke that method and we get a response. I just, again, want to emphasize that we're going to look at this sort of single agreement thing, building block, as something that we could build on to do more complicated things. We can then build, use files and directories, and we can build a ledger by agreeing on the next element to append to the ledger at every time, and so on. So we can build very complicated storage objects with complicated semantics once we have this. Consensus is universal, so anything we want to build, we can build using this. Any object we want to build, we can build using this primitive. So let's just focus on trying to build this primitive. So here, the starting point for this is the end of the previous half. We have an asynchronous shared memory system. We already have the atomic read-write registers, which we saw we can emulate. Can we solve consensus? We already discussed the answer to this. The answer is no. Consensus is not solvable. This is the shared memory version of FLP. It's not solvable if there are failures, but it is solvable if we have eventual synchrony or failure detectors. And this is what we're going to do now. Now we're going to add into the system back what we need in order to make consensus solvable, which is the eventual synchrony or the failure detectors, and we're going to solve consensus, but instead of doing it directly in message passing, we'll use the shared memory building blocks that we already have in order to solve it in shared memory. So I suppose a few of you are familiar with Paxos. Maybe we can do a background poll in Telegram. What percentage of people are familiar with Paxos? Or
Okay, I'll do that.
Yeah, to see how many people know how this works. I'm gonna show you Paxos in a little different way than you're used to, because instead of building it in a message passing system, I'm going to build it in a shared memory system, which means we could build it in a message passing system if we first use ABD to emulate the registers. But now I'm going to assume that we have the registers already, like the ones that we emulated by ABD. And as we established is required by FLP, we're going to use some kind of a failure detector oracle. This is called Omega in the literature. Omega is a failure detector that just selects a single leader and ensures that eventually there's just one process that thinks it is the leader, and then the system makes progress. And this can be implemented with eventual synchrony. So right now we're going to assume that we have it. And once we're going to assume that we have this omega failure detector that is going to ensure the leader is unique, we're going to solve consensus between any number of processes, okay? So it's not going to tolerate just a minority of failures, it's going to tolerate all the way up to n-1 failures. As long as we have one correct process, that process will be able to make progress. This might be surprising because we know that in an asynchronous system, we need a majority to solve consensus, but we already used up our majority in the emulation of the reliable register. Maybe this will be clearer later in the talk when I'll get to that point, but the idea is that we have clients and servers, so we use a majority of correct servers to emulate the registers. Now we have the registers, we solve consensus among the clients that access these registers, and any number of the clients may fit. So now the processes are like clients. Okay, do we have hello?
Yeah, it did. So yeah, we have a poll results. We have 7 votes, 4 of them saying yes and 3 saying no.
Oh, okay. Only 7 votes. Okay. I think there are more people there, right? Okay, so whether you're familiar with Paxos or not, this should be self-contained. If you're familiar with Paxos, you'll see it from a different angle, and if you're not familiar with it, then you got an introduction to it, and then now you can go with the real Paxos, the message passing version of Paxos. Okay, let me just
8 votes. 8 votes. Split.
Sorry? 8? Oh, it's split, okay. So it's split, so I'll try to make everybody happy, both the people who know Paxos and the people who don't. So just to clarify against this thing about the failure detector oracle, okay? Again, we cannot solve consensus. Now we're going to try to solve consensus, not a register. We cannot solve consensus in an asynchronous system without an extra assumption. The extra assumption we're going to make is that we have this module, which we call an oracle, which tells everybody who the leader is. Okay, so I have this module, every process has this module, and it tells them this is the leader, or you are the leader, or you're not the leader. And this module, initially it can make mistakes, it can tell nobody is the leader, or it can tell one person that, X is the leader and another person that Y is the leader. But eventually there is going to be a point in time after which it's going to it's going to identify the same process as the leader, and only that process is going to be the leader. And then once there is a unique leader, the system is going to make progress. So this is the standard progress guarantee of protocols like Paxos and protocols in the eventual synchrony model. And in fact, a leader oracle is the weakest possible addition that we can make to an asynchronous system in order to render consensus solvable. This was proven by Chandra, Zilakos, and Twig. Okay, so this is the weakest thing we can enhance an asynchronous system with in order to make consensus solvable. Okay, so now we have this oracle, and every node knows whether it's the leader or not. It doesn't know if the leader is already stable or not, but it can behave accordingly. It can ask, if I'm leader, do something. If I'm not leader, do something else. Eventually, there's going to be only one leader. The algorithm is going to use registers, but it's not going to use atomic registers as we implemented in the previous part of the talk. It's going to use weaker registers that are called regular registers. Regular registers are almost as strong as atomic registers, but they're a little bit weaker. This is also the definition of regular registers is due to Lamport in a seminal paper that he wrote on interprocess communication. We'll find different semantics for registers. So he defines safe, regular, and atomic registers. And so far we talked about atomic registers. Now we're going to move one step weaker and talk about regular registers. What is a regular register? A regular register ensures that the read returns either a value written by an overlapping write or the register's value before the first write that overlaps the read. I know this is a mouthful, so let me try to explain it a little bit more slowly. So first of all, we're talking right now about single write registers. So we don't have overlap between writes. But the read, it can overlap many writes. It can overlap no writes at all, but it can overlap many writes if the writes are very fast and the read is very slow. And multiple reads can overlap the same write just as well if the reads are fast. If the reads are fast and the write is slow. So every read has to see some value that is concurrently being written concurrently to it, or that was the last value written before all the concurrent operations began. Okay, so this is what it looks like. Okay, if we have the write 0 here and then the write 1, then the reads here, both the blue and the green reads are concurrent with the write 1. They're both allowed to return either 0 because that was the value of the register before they began, or 1 because this is the value of an overlapping write. And both values are legal. Okay, and as you can see, this is an example that we saw in the previous part of the talk. This execution is actually not linearizable. Okay, a regular register, the second read, even though it follows the first read, the green read, even though it follows the blue read, is allowed to return 0 because the rules of the regular register just says it has to return either the write that completed before it began or any overlapping write, but it doesn't have to be in order on the read. So this is not linearizable, but it is regular. Why is it important that we need regular registers and not atomic ones? Well, you should remember from the first part of the talk, we'll get back to that, but you should remember that there was an extra cost to making things atomic. So it's going to be cheaper for us to implement. But we'll get back to that. So for now, all we need to know is that we have regular registers, not atomic ones, okay? And we have regular registers, and we have this oracle that tells us if we're the leader or not, and we're going to solve consensus. Consensus, Paxos uses basically 3 variables. The first variable is called the ballot number. It basically runs votes, and the votes have subsequent increasing ballot numbers. This is a terminology from the original Paxos work by Lamport. So we're going to try to agree in ballot number 1. If they can't, they're going to, the leader of ballot number 1 is not going to bring agreement. They're going to try to agree in ballot number 2. If that leader is not going to succeed, they're going to try in ballot number 3, and so on. So there's the ballot number. And then there are 2 additional variables. Accept value is the value the process was going to decide on. It already accepted it or committed to it and is ready to decide upon it. And the accept num that accompanies this accept value is the ballot number in which this accept happened. The protocol has 2 phases. First, the ballot is initiated, and then there is the accept. So if we run the second phase, we update the accept value and the accept number in the second phase, so the accept number matches the ballot number. And when we run the first phase, we increase the ballot number. So this is true for Paxos in general. If you know Paxos, that's basic variables it works with. The shared memory version just stores these in shared regular registers. All the registers that the algorithm uses are single writer registers. So every process has its own registers that it writes to, and then it can read everybody else's registers. Okay, and maybe I'm not sure I emphasized this, but I think so. This second bullet here, we use single writer multi-reader regular register. So every process is going to have a single writer register that it writes to, and anybody can read it. Okay. X subscript I, that indicates the single writer register to which only process I can write. This is process I's regular register. It's going to be a quadruple consisting of 4 fields. The first one is going to be the ballot. Process I is going to increase this ballot number every time it participates in a new ballot. The next 2 are going to be the accept value and the accept number. So process I is going to write to these if it runs the second phase of consensus. If it commits to value, it's going to write the ballot number and the value in these fields. And the last field is what the process decided upon once it's decided. So when the protocol ends, this will include the decision that the protocol has reached, the consensus decision. Okay, so these are the variables. When we start off, the ballot number is 0, 0. Why is it a pair? Why is it not an integer? Well, you may remember from when we talked about ABD, and I said we need to break ties by process ID, so the same is true for Paxos. So the ballot number is going to be a pair where the first element of the pair is a monotonically increasing counter, and the second one is the process ID in order to break ties. So my first ballot would be 1, Idit. Okay? And then since we haven't decided anything yet, the decision value is going to be bottom. The ballot, the accept num and the accept val are also going to be bottom and 0, 0. Okay, and each process has local copies of these values, which it maintains locally and then uses to write the global memory. How does the protocol work? Well, every process asks itself the question, am I the leader? It goes to its oracle, this omega oracle, and says, am I the leader? And if he is the leader, if it is the leader, it tries to lead to a decision by starting a new ballot. It chooses a ballot that is bigger than all previous ones and that is unique. The uniqueness is ensured by the second field by breaking ties by process ID. And then it goes and writes it to its own register. So the register has 4 fields, right? The first one is the ballot. That's the field that's changing right now, okay? And then the other fields, they're unchanged. That's why I said every process has these local copies. So whatever they were before, that's what they stay. They're not changing. The only field that changes in the register right now is the ball. And for those of you familiar with the Paxos algorithm, in the Paxos algorithm, the leader sends a ballot number to everybody. So here, instead of sending to everybody, we just write it. We're not sending messages, we're writing to shared memory. And then after writing the ballot, it goes and reads all the registers of the other processes, okay? In the message passing version, we would have waited for acknowledgements that we managed to write to them, but now we're not waiting for acknowledgements, we're just reading. Because we're not talking directly to the processes, we're only using shared memory now. If when the leader reads, if it finds a ballot number that is bigger than the ballot it proposes, then it starts over. Meaning it stops it stops this current ballot number and it goes back to the beginning of the code, to the top of the code, and sees if it can try maybe with a bigger ballot, or maybe if there's another leader, but it gives up, kind of aborts this current instance. But if it doesn't find anyone bigger, then it knows that it can try to reach a decision. And when trying to reach a decision, there are 2 options. One option is that it finds that somebody has already tried to reach a decision before. And that is in the val field. Somebody already committed to a value, that somebody already wrote that they accept the value in the second field of the register. And this is the else case here, right? So if it sees that somebody already proposed a value, then it chooses the one associated with the highest number, and it adopts it. It's going to propose this value. And if nobody, the second case, which is the first case of the if here, if nobody proposed a higher value, okay, they're all bottom because nobody already reached the second step of the consensus protocol yet, then it just takes its initial value, the value that consensus was invoked with, the proposal was invoked with, and it's going to propose this value instead. Okay, so at the end, just to recap what's going on here. If the process is the leader, it's going to try to reach consensus. It declares that it's about to reach consensus by writing a new ballot number. It then checks if anybody started a higher ballot. If anybody started a higher ballot, it gives up. Okay, it doesn't try. If nobody started a higher ballot, it's going to select a value to propose for consensus. There are 2 options. Either somebody proposed the value before, and then we're going to adopt the one that was proposed with the highest value before, or all the values are bottom, meaning nobody proposed a value, and then the process is going to propose its own value. It's going to try to reach agreement on its own value. So this is the first phase. In the classical Paxos, normally what you have is a leader chooses a new ballot and sends a message to everybody. What we have here in the shared memory version is the leader chooses a new ballot and just writes it to its variable. In the classical Paxos, when the leader sends the ballot to the processes, they send an acknowledgement if this is the highest ballot they've seen. So if they're not in any later ballot, they say ACK. They say, the leader says, I want you to join me in ballot 7. And if none of them moved on to ballot 8 by then they go and they say, ACK, we're joining you. What's going on here? Well, here the leader doesn't send a message to anybody, it just reads. But it reads their registers and it makes sure that none of them moved on to a later ballot. Okay, one subtle difference here is that in the classical Paxos, the leader waits for acknowledgments from a majority because we tolerate failures of any minority. And here the leader reads all the registers, all of them, because the shared memory is reliable, even if processes fail. So it can read the registers of all the processes. Okay, the register lives on after its write-up process fails. That's what we got from using ABD. So this is the distinction made here, okay? And if this is successful, we move on to phase 2. So in the second phase, the leader changes its accept number, which is the third field of the register, to be the ballot, okay? And it tries to write it. Remember that B was determined in the first phase. V, which is the second field, was determined in the 2 slides ago when we chose either the value that we saw with the highest number or our own initial value. And N is now set to be equal to B. So we're indicating that the value V is being committed to or accepted in this ballot B. And the decision still remains bottom because we haven't decided yet. Again, the process writes it to its own register, whereas in the classic Paxos, it would broadcast it to all the processes. So in this phase, the fields that changed are V and N, the accept num and the accept val. Again, the leader reads all the values. And again, if it sees that some process started a higher ballot, then it starts over. Okay, it's exactly as in the first phase. And basically, it reads to see if anybody would have said, no, we're not accepting your proposal because they're in a higher ballot. Okay, because leader processes don't accept the proposal if they're in a higher ballot. And finally, if it didn't start over, if it didn't find anybody competing with them and nobody has a higher ballot, then here it decides. Here now, the only field that changed in the last write is the last one. Change the decision to V. So now we can return V, we have decided, and any process that comes later on will be able to see that V has been decided. This is the way the protocol looks. We have 2 threads that both think they're leaders because the failure detector, it may be unreliable for some period of time before it chooses a unique leader. It can tell 2 people they're a leader for a while, and then eventually will tell one of them that it is the leader. So here we have 2 threads, the red one and the blue one, or 2 processes, the red one and the blue one, both thinking that they're leaders. And one of them has a bigger ballot than the other because we know that the ballots are unique, so they don't have the same ballot. So in this case, the red one has a bigger ballot, B prime, whereas the blue one has the smallest ballot, smaller ballot, B. And they both go and write the ballot number. And then they both read. And then they try to write for the second time, and again they read. Okay? Well, what we know is that because the writes overlap here, and the write of B prime doesn't complete before the read by the blue thread, then we know that it's possible for the blue thread not to see B prime. Okay, if the blue thread would see B prime here, it would abort. It wouldn't try to reach consensus, right? But because there might be an overlap between the writing of B and B prime, then the blue thread might miss B prime and might continue to the second phase. So we might have a scenario of two processes here concurrently running, the red one and the blue one, both of them thinking that they're the leaders, both of them trying to reach agreement, and both of them successfully passing the first phase. The blue thread succeeds to go through the first phase because it doesn't see the red thread, and the red thread successfully goes through the first phase because the blue thread has a smaller number. So it doesn't see, neither one of them sees a bigger ballot. That's why we need to do another read in the other phase. Okay, now they might write conflicting proposals. The red thread would propose one thing and the blue thread would propose another thing. They both are trying to propose things here because neither one of them saw the other. But then comes the second read after writing the accept num and the accept val. And here the red thread sees that it hasn't been superseded because it has the higher ballot. So it decides, whereas the blue thread sees that it had been superseded because now it has to see B prime. The second read does see B prime, sees the first write of the red thread, and it doesn't decide. So I think I've talked for a long time now and it might be complicated. I think it's good time to stop for questions. I didn't say what the non-leaders do, but right now I just want to make sure that it's clear that if two processes think that they're a leader, then we don't take conflicting decisions. And if there's only one process and it is the leader, then it is deciding.
Ivan, do you hear us right now? Okay, so it seems Ivan is not here. There is no questions in the Telegram chat right now, unfortunately, but I wanted to ask, I'm not sure that I understand fully why there is no possible that the red processor, like his second write, will be longer. Why it's like, I don't understand fully the proof. Can you probably give a brief explanation of the proof?
So first of all, this is not a proof. This is an example. Okay.
Yeah, this is example. Yeah, I understand. But can you give me give some intuition why it's true?
Yes. Yes. Again, so the second write, it could be longer. Okay. If you look at this example, let me try to again annotate this. Okay. So this write, okay, the second write, it might overlap the second read. Okay.
Mm-hmm.
But the problem we have, but this read will see this write.
Yeah, but okay. If the first write was very long, like if the first write
would be very long, yes. If the first write would be very long, then this read would see this write. I'm going to go over and to get the proof to the proof before. But if this read, the last read, this read will not see this write, then this write, then this read will see this write.
Oh, like this write kind of commits their information that it has chosen their value.
Yeah, it's going to make sure that it sees it. Yeah.
Okay, I see. Okay, thank you very much. Now I understand.
Okay.
What's
I'm going to go over the proof. This is just an illustration, but just to, I know it's a little complicated, but that's basically the protocol. So are there any more questions or?
No, unfortunately there is. It seems people are kind of tired probably already, because like, you know,
okay.
it's 2 hours for like almost 3, so.
So I defer the hardest thing to be later, but okay.
I hope that everybody understands. So like, if you have any questions, please ask right now, because like otherwise we will move forward, and it seems it will become more will become more complicated then.
Yeah, no, I can go back later whenever you ask questions. I
Okay,
can go
sure,
back.
sure.
That's no problem.
So let's agree on that. So if there
Okay.
will be question, I will just interrupt you to ask.
Yeah. Okay.
Thanks.
So let me just complete the algorithm. So the algorithm, I gave you the leader code. The leader code, the full algorithm works like this, right? Basically, you execute an infinite loop until you decide. And if your oracle tells you that you're a leader, then you try to reach a decision by basically writing, reading, writing, reading. And that's what you do. And if you're not the leader, then all you do is wait for the leader to reach a decision. Okay? Just go and read the leader's register. And if you find a decision there, you return it. And if not, then you sit and wait quietly until the leader decides. Okay, if the leader will fail, then Omega is supposed to elect another leader. So Omega is going to ensure that in the end, there is one leader that is going to reach a decision and everybody else will decide. So let's talk about liveness of this solution, okay? The shared memory that we're using is reliable, okay? Everything that's written stays there even if the process that wrote it disappeared. The readers, the registers are all there even if their owners never showed up, okay? They don't have to be around. And this is actually a very appealing model for, if you think about it, we have a storage system, we have multiple clients that access it concurrently. You want to make sure that they don't do conflicting operation. If only one of them shows up, it's the leader, and then it could just do whatever it needs to do, and it solves consensus on its own. The leader might not succeed, right? Because it has this start over in the code. Okay, the code has this. The reason why we might lose liveness is because we have this right here. We have start over, okay? Because of this. This is the only thing why we might lose liveness. The only thing that might cause us to lose liveness. But if we have only one leader, then nobody will compete with it, and then it will not fail. So the only reason why a leader will not succeed is if there is another leader competing with it. So what Omega needs to do is ensure that there is only one leader. So in a shared memory system, this Omega thing is sometimes called the contention manager, something that ensures
Idit,
there is no contention. Yes.
can you hear me? Yeah, there is a
Yes.
question coming from the chat room. So
Welcome back.
as it says, yeah, thank you very much. There was technical issues. As it says, you mentioned earlier that leader could only get proposal from elsewhere, but for no reader case, the readers read from the leader register. So how it could be that the others propose values?
Okay, so that's a good point to clarify. The leader is the only one that proposes values. If the leader finds proposal by others, that means that the others at some point thought they were leaders, okay? So it's not that for the entire duration of the protocol from the beginning to end, there is one leader. We have this Omega thing. It's kind of its contention manager. So there are processes coming in, and there's two processes coming in. First, they both think they're a leader. So they're both writing proposals. And then one of them kind of detects the other and stops being the leader, and then the other one is the leader. So then the leader will see the proposal of the other process from the time when that other process thought that it was the leader. Okay, does that answer the question?
So basically, it is possible when two phases do overlap in terms of time. Is that correct?
Yes, it's correct. This is an example, right? in this slide, we have an example. We have two processes, and they both think they're leaders. So it's possible if a leader sees the proposal of another leader, that means, yes, that there was some overlap. There was an overlap between these two processes trying to run their operations, and there was an overlap between the time that both of them thought they were leaders. And that's why the one of them will end up adopting the value that is proposed by the other. But then
Thank you very much for the clarification.
A leader decides, yes, once a leader decides, then all the others read its value and adopt it. So we'll talk about this contention manager again in a few minutes, but the liveness, as long as we have multiple readers, we might not have liveness. Once we have a single leader, that's when we get liveness, okay? We can't hope for anything better than that because of FLP, okay? FLP says that if you don't have anything that controls who thinks he's the leader at any given time, then you can't solve consensus. That's I guess the point to understand here. But once that omega thing works and it makes sure there's one leader, it's only eventually then that leader will succeed and the others will be able to read its value. So let me try to argue that the other properties of the protocol are correct. So validity is the easiest one, okay? The validity means that we're only going to decide on the value that is proposed by one of the processes. And validity simply holds by induction on the steps of the protocol, because the leader always proposes either its own input value, which we know it's valid because it's its own input, or a value that was previously proposed by an earlier leader, okay? Which by induction means that it's always a value proposed by some process, okay? Now, I want to point out here that we're not using atomic registers, but that doesn't matter because we're still only reading values that were written. It might be that a leader would read some value and then a later read will read an earlier value because regularity allows values to be ordered, but we don't care. So I'm just pointing this out because we made this, people are used to registers being atomic or shared memory being atomic, and here it's not. It's just regular. And what I'm telling you, just notice it's fine. The shared memory regular, but it's fine, at least for validity. Let's talk about agreement in a minute. So agreement is a little more complicated, and I'm again going to try to illustrate it by example. So let's say we have some process, this is the blue process, that actually manages to be the leader and reach an agreement. So it writes with some valid B, it reads, it doesn't see any value bigger than B, it writes a proposal V, it doesn't really matter where V comes from right now, and then it reads again, and again it doesn't see any valid higher than B, and it writes the decision. What we want to make sure is that if there is if any thread starts after this is over, then they just read the blue thread's value and we're done, okay? But we want to make sure that if something has happened concurrently with this, another leader concurrent with this, they will not write a conflicting decision. Okay, so the thing to point out here is that in the second read, this thread doesn't see any bigger ballot. That means that if there is any other process that is going to run the same, also think that they're the leader, go through the same steps with a bigger ballot, they're going to have to do it after this red line, this red dotted line, okay? They're not going to be able to complete before their first write, okay? The first write of their algorithm before this dotted line, okay? This is not possible, okay? The scenario drawn here. Sorry, this is possible, but this is but it's possible for the write to overlap, but it's not possible for it to complete earlier. Okay, and that means that the read. So we have this read process. Okay, this read process. This is the first write, the first phase, just the write of the ballot. It must overlap the blue read, and this means that the read, which is invoked after this write, will see B. So if the second process thinks that it's the leader, it's going to find V in the register when it does the read. And it's not going to propose its own value. It's going to propose this V that the blue reader suggested. Okay? And then in the second write that now happens, it's going to write the same V. And then if it manages to reach a decision, it will decide on the same thing. This is the illustration of a wide proof. I think this is what Vitali asked me earlier. What happens if the first write is overlapping the second write of the blue process? Then the red process will see the blue process. Okay, and if it's not, then it's the other way around. Okay, let me just try to formalize it a little bit. I'm not going to write a really formal proof here, but basic idea to prove, you do this, you ask yourself, what is the smallest ballot B in which some process decides a value V? Okay, and the first thing to observe is that ballot numbers are unique. Remember, we broke ties by process ID, so we don't have the same ballot twice. There's only one process that's going to propose values with the same ballot, so it's not possible for any different value to be decided with the same B. So now we're going to prove by induction that if any decision occurs with a ballot number B prime bigger than B, it's going to also be V. Okay, and that's, I'm not going to show how that works, but basically it uses this argument. Okay, we have the blue process deciding here, and the red process is going to propose the same value as the blue process. We're going to show that by induction, but I'm not going to do the formal proof. Again, back to Leibniz termination, the Leibniz property of consensus. When there is one correct leader, it eventually chooses a higher ballot number than all those that were written before, because it keeps trying, it keeps increasing the ballot until it succeeds. And then because it's the only leader, then nobody competes with it. And so nobody writes a higher ballot. And so once nobody competes with it, it doesn't start over, and then it decides. Okay, the thing to note here is this is completely independent of other processes. The other processes don't have to show up. This is really good for a distributed storage system where we've used the servers to emulate these registers, and now the client shows up, it can read the registers. Every client has their register, but the clients don't have to show up at the same time. Everyone can show up when they want, and they can reach the next decision. They can use it to make a decision on whatever change they want to the shared file system, and so on. So can we see if there are any questions or things that you would like me to clarify?
So far, the chat room is good. On my side, I would propose to reiterate on how we can formulate the inductive invariant here, if it's possible to do briefly, because usually that helps to gather the proof idea.
Yeah. Yes. So we formulate this by basically we're saying that for every ballot number greater than B, if there is a decision, the decision is B, and we prove it inductively. This is like a complete induction. It's a sparse induction, right? We take the first So B might be 7 and B prime might be 17. There might be gaps. But then we look at the first ballot, bigger than B, where this could happen, right? Where there could be a decision. And then by complete induction, we know that in all earlier ballots, there was no decision different than V. So in all ballots smaller than B prime, there was no decision different than V. This is sort of what we know inductively. And then we show that because this is the only decision, we see this decision in the accept val, and we show by induction that there's never anything in the accept val that is with a higher number than B that conflicts with it. Okay, so there's never going to be any accepted value bigger than B in the V in the oh, let me say it a little more slowly. We have this
in the output
pair
register.
We have the pair. We have the pair V and N, like the accept val and the accept num. So there's never going to be any value accepted. We're going to show by induction that there's never going to be any value accepted with a ballot number greater than B that is not V. Every time there's going to be a VN pair in this the circle, the thing with the blue circle here, the VN. Anytime there's going to be N greater than that B there, it's going to be with the same value that's been decided with this V. We're going to show this inductively. And the argument is going to be that whenever a new leader, after V has been decided, is going to propose a value, it's going to see this, and this is going to therefore remain the only value that has a higher. It's going to see that value with B, and then subsequently V is going to be the only one written with the value bigger than B. I hope this was not too confusing.
Okay, thank you. So far, no extra questions on the chart, inside the chart. So yeah, I believe we can continue because the proof looks quite similar to the Paxos proof. Yeah, and if somebody needs any so if somebody needs any extra details, it's always possible to come back to the Paxos proof and try to reformulate it and apply it to the described algorithm. Okay.
That's right. Thank you. It is similar to the Paxos proof, and also it appears, I can give the reference, it appears actually in our paper on Byzantine disk Paxos, the proof appears there for the shared memory version of Paxos. So one thing that I want to point out is that we have two writes, but the first write, the write of B, doesn't write consensus values. So anybody who's familiar with Paxos would know that if we have a leader running multiple consensus instances, they can do the first round, the ballot election once, and then do the second round many times. This means that if we have like think of it as a client that's coming to do some operation on the shared file system, and it succeeds to do the first write and doesn't see a higher ballot, it can continue to do the second write multiple times for all the consensus values. It never needs to go back to the first write unless it sees a bigger ballot number. Okay, this is an optimization. Okay, so basically, once I do the first read here, the go back to this, right? But basically, I could do this just once, and once I've done this and I have a ballot, I could just repeat this part for many decisions until I'm superseded by another ballot. And once I'm superseded, I'm going to have to try to find a higher ballot number. But as long as I don't increase the highest ballot number, I can continue to do the second time as many times as I want. So it's quite efficient, actually. Okay, the ability to make decisions. Okay. So let's go back to omega. How do we get the omega? For omega, we need an eventually accurate leader. Okay. So as I've sort of briefly mentioned before, this is not a message passing system where we're trying to find one process to be the leader. This is a shared memory system where we have multiple processes accessing the shared memory. Basically, when we want one process to access the shared memory, we normally call that mutual exclusion, right? We want mutual exclusion. If there's one leader and there are no other leaders, then we have mutual exclusion. The difference between mutual exclusion and what we're trying to do here is that it's not fault tolerant. Okay, if we take a lock and one process takes a lock and that process fails while holding the lock, then no other process can succeed to access the shared memory at the same time or forever again because that process failed. It's not fault tolerant. So basically what we want is some kind of a fault tolerant version of mutual exclusion, which is not perfect, but only eventually fine. Okay, so it's fault tolerant and kind of time restricted. This thing is sometimes called a lease. It's a kind of a lock that is live and not safe. It eventually ensures mutual exclusion, but not always ensures mutual exclusion, but eventually in the eventual synchrony model. So basically, if we wanted to put this all back together, we want to use this in a storage system. So whenever a client has something to write, the client tries to obtain the lease. Okay, and once the client holds the lease, it's the leader. And then if it fails, it fails. But the lease is time bounded. So once the lease expires, other processes can use it. So one way to implement this is to use just backoff. So the client tries to get the lease, it sees that there are other clients competing with it and suggesting ballot numbers bigger than its own, then it says, okay, I'm going to wait 1 minute. Comes back, still sees competition, it can do exponential backoff. It can say, I'm going to wait 2 minutes. That doesn't work. I'm going to wait 4 minutes or some random time between 0 and 4 minutes if I want to stagger the processes. And leases usually have a limited duration. So process grabs the lease is taken, they wait for the lease to expire, and then the others compete on it. So that's kind of a summary of the difference between locking and leasing. So if we have a lock, it's blocking. Using it is not wait free. If the lock holder fails, we're in trouble. But it's always safe. We're never going to have two leaders competing, two processes trying to do the same operation. We wouldn't need shared memory Paxos. We'd be fine, okay? But if we want to be non-blocking, we could use a lease. The lease is not safe as itself. It might lead to there being two leaders, but it's fine because we're using Paxos to solve that case. So we're ensuring that even if there are two leaders, we're not going to get into trouble because they solve consensus. So again, if there are any questions, please stop me. I'm getting a lot less feedback in this session than in the previous one, but this is the idea. Just maybe to clarify this, the lease is how we use this Paxos. So the shared memory Paxos. So the complete system is we have the shared memory Paxos, and then we have the leasing mechanism that ensures that we have only one leader eventually competing in shared memory Paxos. This Paxos is basically a combination of everything we've seen so far. It's consensus using n fault-prone disks. Okay, shared memory Paxos used n reliable registers that were not fault-prone. Now we're using fault-prone disks where, yes.
Yeah, before we jump to the disk Paxos, there is a question coming regarding, this slide on locks and leases. The question is that true to say that leases are like optimistic concurrency?
Leases can be used for optimistic concurrency. Yes, yes, exactly. That's what we're doing. We're using optimistic concurrency here. That's exactly what we're doing. Okay. We're being optimistic. We're hoping nobody competes with us, and if they compete with us, then yeah, that's a really good observation.
And one more question, maybe a bit more of a practical matter. So practically in implemented memory setting.
Sorry, you were cut off. I couldn't hear.
1, 2. To repeat, a bit of more practical question, how can you implement a lease mechanism in a practice?
Yes, so that's what I wrote in the previous slide. You could use a backoff, for example, or you could just do backoff. That would give you basically this. Or the other thing you could do, you could just use a timer, and even if it's asynchronous, even if it's not accurate, I can just write somewhere that I want the lease until this time, and then you go read and you see that somebody else asked for the lease, and then you do a back off and you wait for this time to expire. And if you miss what I wrote because there's contention, then we both try, and then we see each other, then we both fail, and then we do a back off. So that's the idea. You do some kind of a back off.
Yeah, so there is a extension to this question about the implementing the leases. Maybe it's worthwhile explaining Linux in a bit more detail. The question is formulated like that: how we can build a fault-tolerant lease in such a way that different processes will agree on whom has the lease actually. So maybe you can clarify the purpose of the lease mechanisms, and if this is a good post question or a bad post question.
So I guess the important thing to remember is what we're up against. Okay, we're up against FLP. Okay, if we could implement mutual exclusion, or we could implement in a completely asynchronous fault-prone system, we could implement mutual exclusion, we would be violating FLP, or we could solve consensus, we would violate FLP. So we can't have a bulletproof solution. The idea of the lease is that if you do a back off, then if the process grabbed the lease, they're not going to hold it forever because it expires. So the process said, I want the lease, the process fails, they keep the lease until the timer expires, then the others can compete for it. But if there are others compete for it and they don't really back off properly, they just keep contending with each other, then they'll never succeed. So theoretically speaking, if it's completely asynchronous, we can't guarantee anything. Practically speaking, back off works. That's how you do also contention management in distributed transactions, or in competition on other things. That's how Ethernet works. You try, and then you see somebody else has tried and collided with you. Then you take a step back and you wait some time, and then you try again. And so that's the way you do it.
Thank you. Personally, I would like to add that leases, they act like an attempt, so they do not provide any strict locking guarantee, but rather than a weak key that I'm attempting.
Exactly. That's why I wrote here that. Yeah, exactly.
Yeah.
That's why I wrote here they are not safe.
It seems that. Yeah, it seems that we have agreement here. The questions, there are no more questions outstanding inside the chat. Continue to the disk access. Thank you.
Okay, great. So this Paxos is basically putting together things that we've seen so far. First we said we want to emulate a register from fault-prone servers. Then we said we have this reliable shared memory and we're going to solve consensus. Now this Paxos puts them all together. So we have M servers or disks for that matter. The servers can be disks because they don't talk to each other. Only the clients access them. And it says here 2t+1 because I don't know why I changed F to T, but a majority of them are correct. So it's bigger than 2F+1, where F is the number of failures. So now they can fail, okay? And the M is going to be the number of clients and N is going to be the number of disks. So we're going to have a M process shared memory Paxos running on top of these full-prone disks. So we're going to combine the shared memory Paxos with the ABD emulation. Okay, so this is what it's going to look like. We have these M processes. We have kind of a matrix, right? And we have 3 disks or servers. And in each server, we have a copy of each of the processes' registers. So in this example, we see the registers belonging to process 2. That's what we call X subscript 2. It's, yeah, I wrote this here. Actually, I don't know if you see this, but here, X subscript 2. That's what we're seeing here. It's copied 3 times, 1 on each disk. Okay, we have N is 3 here. So we have 3 disks, and this register is copied on 3 disks. Only process 2 writes to this red strip in all 3 disks because it's a single writer register. And process 2 can read all the blocks in all the disks because it's a single writer multi-reader register. This is what we needed for the shared memory Paxos. Now, what we're going to do is we're just going to combine the two. So if we take the shared memory algorithm, it has a read loop. Go read all the registers. Each one of these reads gets translated to this code. Go and read the relevant block in all the disks. Issue a request to read the relevant block in all the disks. Wait for a majority of the disks to respond, and then choose the one with the maximum. This is what we did for reading in ABD. And now comes the question, is this enough? Is this all we have to do in order to emulate the read for shared memory Paxos? Okay, so again, to rush back a little bit, but we had a shared memory Paxos algorithm where we had in some places we had like here, for example, we have here, right? Read all XJs. Okay, and we have it in other places in the algorithm. We're reading all the XJs. Okay, so now I'm telling you how this read actually works in the distributed storage where the disks can fail. And this is how it works. It goes and issues a request to read for all N disks, waits for a majority, which is N minus F, and chooses the maximum one. And my question is have we done enough to emulate a read? Or is it good enough for us to do the reads this way? Is that how we did it in ABD? And if not, is that a problem? That's my question. Get an answer to that. So.
ABD mechanics with the timestamps, so I wonder if it's need to be applied here as well, or spell it as a timestamp.
Okay, right, exactly. So in ABD we had timestamps, and here we use the ballot as the timestamp. Is it okay to use the ballots as the timestamps? Yes, because they're monotonically increasing, and that's all we needed in ABD. But okay, I understand the channel is pretty quiet now, so I could just say it if it's not.
Yeah, maybe it's worthwhile to describe in a little bit detail what
Okay.
may go wrong. So in the recording, the students could go once again over the explanation, because yeah, as Vitaly suggested, by the evening, I believe a lot of people are tired right now.
Yeah, okay. Okay, fine. So I just want to remind you that when we did the read emulation in APD, we did a write back, okay? I don't know if this wasn't a very long time ago, but maybe you remember this, but we needed a write back. When we read, we couldn't just read. We had to go back and write what we read. And the reason we needed a write back was to prevent scenarios like this one, okay? In APD, if we did the read without the write back, then this is possible. But fortunately, in this Paxos, we only need regular registers, okay? If you wanted to know why I made a point of this, that the registers are regular at the beginning, this is the reason, because it's actually saving us around. Because it is okay for us, for multiple readers, not to be order. The only thing we used in the proof was that the order between reads and writes. We never used anything about the order between reads and reads, but by different processes. So it was fine for us to have this non-linearizable scenario, and that's why it is okay to do the read emulation just like this. Okay, so we got a discount here. ABD does a read and a write back, but we don't need the write back. Okay, and the write emulation, every time we have write in shared memory Paxos, we issue a write to all the disks and wait for majorities. And again, I ask, this is enough? But the answer is yes, it is enough, because if you remember in ABD, we only needed the initial read if we wanted a multi-writer register, and here all the registers are single writer. So in fact, we get a very lightweight version of ABD. We have the write only writes to a majority, does not need to read, and the read only reads from a majority and doesn't need to write. So to summarize this part, we emulate reliable shared memory using ABD in asynchronous systems where a minority of the nodes can fail. Then we use shared memory Paxos to solve consensus in asynchronous shared memory that is reliable, that is atomic shared memory registers that are not fault prone, using a leader election failure detector and targeting any number of client failures. And then finally, this Paxos combines the two. So we run the shared memory Paxos on top of an ABD-like emulation, but with a discount. ABD with a single round for read and a single round for write.
Idit?
So that's, yes.
Yeah, there is a question coming from the chat room, especially regarding the Discord combining the two. Could you please once again cover the part why it matters to algorithms? So we need to combine them. How they are linked? How do we link the ABD algorithm and the shared memory? Why it's necessary? This to cover this, we need to go over the problem statement once again.
Yes. Okay. I guess I didn't really tie that very well, but let me just kind of, because it's getting late, try and remind you what we had at the beginning of the very beginning of the talk, and maybe should have a recap of it here. But whoops, this is what we wanted. Okay, we have all these end servers, and f of them can crash. Okay, and we have these clients, call them M clients, but we have lots of clients, and any of them can crash. This is our world. In our world, we have in the cloud, in the data center, we put N servers or disks or smart disks, and F of them can crash because we can have failures in the cloud as well. And then we have all these clients that are completely unreliable and they can crash. And what we want to allow these clients is to do some operations on the shared storage. So ABD allowed us to implement the illusion of reliable memory, but only read-write memory. But now these clients want to do something more complicated. They don't want to just read and write to memory. They also want to do a file system, and then they need to be sure that if they create a subdirectory, then there are no two different subdirectories with the same name, or they need to ensure some other thing that requires consensus. To make some operations to make sure that no two nodes delete the same file or create two files with the same name or whatever. So they want to solve consensus also. So what we did in this Paxos is we allowed them to take the registers that they emulated via the reliable emulation and to use them to solve consensus when they need for liveness some kind of a lease mechanism that would allow them to not contend with each other when they solve the consensus. Okay, and what I said about the part about disk Paxos is how it all works together. How when disk Paxos runs on top of this storage emulation, what it looks like. When shared memory Paxos runs on top of this. So because shared memory doesn't really run on a shared memory in this disk Paxos example. The shared memory Paxos, it runs in a setting that looks like this. Whoops. Running. Forward. Yeah, the shared memory runs in a system that looks like this. We have 3 servers here or 3 disks, and one of them can fail, n equals 3, f equals 1. And now we want to write the shared memory Paxos. Now in shared memory Paxos, we assume that we have a reliable register. We can just write to it. Okay, that's how I wrote it in the code here. I just wrote write, right? Read, write. Here, I have this example here. Read. Okay, I have this, and I have similarly, I have write and read. But now, in order to do the write and the read, I need to use my ABD like emulation. So I need to go and implement this on top of many disks. And you could say, well, abstraction, why do I care? Let's just say we have ABD, and ABD gives me these reliable registers, and now I'm going to just use them as a black box. But by opening the black box, I've managed to give you a discount. I showed you that I could do the read in one round and the write in one round, because the read can happen in one round because I only need regular registers and not atomic, and the write can work in one round because I have a single writer. So when I put it all together, I have the clients, they go, when shared memory Paxos tells client 2 you have to write B, you have to change B because you want to start a new ballot, then what it does is really this. Sorry, it is this. Okay, that's how it writes. The implements the write in shared memory Paxos. That's an ABD-like emulation of the. Sorry, that's the read, and that is the write. It needs to write its ballot. That's what it does. That's an ABD-like emulation of the write. So is that clear now? How it all fits together?
Yeah, I think it is clear now. So unfortunately, one went for a T, or I don't know what's happened, but yeah,
okay.
that's clear. Yeah, thank you very much.
But you read the channel as well, right, Vitaly?
Yeah, I also read the channel, so there is no question. Like the people just wanted to already forget. Okay, so there is a question. Would you say that disk Paxos is a good fit for RDMA?
I don't know if RDMA, I would say RDMA is normally synchronous, not asynchronous. So this Paxos is good if you're writing to storage and you have no feedback whether that storage is alive or not. And I think that normally with RDMA, maybe I'm not an expert on the technology, but as to my knowledge, with RDMA, if you know if it's succeeded or failed, so it's not asynchronous. You do an RDMA and it returns, and you know that you managed
So,
to.
so in asynchronous, you have better algorithms, right? It seems then it's quite complicated,
You
right?
could still use this kind of emulation, but you don't need. So, for example, if you're synchronous, you can tolerate more failures. You don't need only a minority of the disks to fail. If you know that you can detect failures accurately, you can have 2 copies to tolerate 1 failure. You don't need 3 copies to tolerate 1 failure. So if you have synchronous communication, you have like perfect failure detection, and you know that the machine you failed to write to is indeed down, you don't have asynchrony, you're not worried about split brain, then you can do better. Then you could get it cheaper.
Okay, I see. I think this answers the question why. So I'm not sure that I understand. Have you finished already the talk with the summary? Because like Ivan interrupted you at almost the end, so I don't know.
So this is the summary of the talk, and I wanted to mention some new directions that are related, but I think it's getting late, so I'm going to just mention that they exist and I'll talk about them. But I think there are 2 things that my group has been working on in the context of these type of algorithms. And one of them is allowing reconfiguration, which is how to change the set of servers that are being used for the protocol. Because so far it was static. We had a static set of end servers. And the second issue is storage blowup, which we tackle by using erasure codes instead of replicas, and some trade-offs that this introduces. So I'm not going to get into these slides. I'm just going to, if anybody's interested, maybe we can do this in the QA tomorrow, and I gave the pointers to the relevant papers in the background material, just to know that there are other interesting things going on. Even though ABD is a protocol from like 20-something years ago, there are newer issues on how to reconfigure the set of servers that the algorithm is implemented on top of, and how to deal with this, how to use erasure codes in this context. So that would be, I guess, my last.
Okay, I see. So
One, two. Can you
oh,
hear
okay.
me?
Ivan is here. Okay, that's very good. Like
Yeah,
right at the end.
sorry, one.
Okay, I wanted
Yeah,
only
just
to
at the end.
I wanted only to remind that their Q&A session will be tomorrow at 3. So you're welcome. Everybody is welcome, and Idit, you also is welcome on this Q&A session. I hope that you will come to it. Ivan will be there, I think, also, right?
Yeah, I'll be there tomorrow.
Okay, great. So Idit, thank you very much for your great talk. I think from my perspective, it was amazing. I hope that viewers also liked it. Ivan, thank you very much for your moderation. Like that was enormous work.
Thank you.
Thank you very much.
Yeah, I would like to add a few more notes if time permits. So personally, I find it really fascinating that usually when you study shared memory parallel computations, you go over the register constructions over the shared memory. But in this talk, we went through the register construction in the message passing model. While for the Paxos, we usually do study the Paxos implemented on top of message passing, while here we studied the Paxos implemented on top of shared memory model. So it was really fascinating to see how we can combine these two approaches and build up something which is applicable for the cloud storage. So thank you very much for this.
Yes, thank you. And you did a wonderful job with moderating this, and I hope people are not too tired, but I'll be happy to continue the discussion tomorrow. So thank you very much.
Thank you.